Hey guys, sorry I couldn't be here today. Today we're going to talk about 11.3, and 11.3 is similar to what 11.2 is about in the fact that you'll be asked kind of the same questions, but about a different type of sequence. This time we're going to be talking about geometric sequences, and in geometric sequences, the numbers constantly go up or down by the same ratio, the same multiple. So geometric sequences are sequences where the ratio in between different terms is constant, and that particular ratio is often called the constant ratio, and we abbreviate that R. And for our formulas, when you see an R and when we write that in there, that's what you multiply by to get the next term. Often to calculate R, sometimes our brains can look at a list of numbers and figure out what you multiplied by to get the next one. But a lot of times you need to divide. So if you look at the next term and you divide it by your current term, that's what the ratio is. And so many of your questions will be things like this. Determine whether a sequence is geometric or not. What that means is look at all those different ratios and see, are you going up by the same amount? Are you multiplying by the same amount each time? So to get from 1 to 2, that's a ratio of 2. 1 times 2 gives me 2. To go from 2 to 6 is to multiply by 3. To go from 6 to 24 is to multiply by 4. And I can already tell that this is not a geometric sequence. These are not multiplying by the same amount each time. This is actually an example of what's called a factorial sequence, but that's not the topic of today's lesson. In this next example, to go from 81 to 27 is maybe not as easy to figure out what you're multiplying by to make that happen. And so here's an example where I might look at what is 27 divided by 81. 27 divided by 81 is the ratio 1/3. And so if I look at the next ratio from 27 to 9, if I do 9 27ths, that's also a ratio of 1/3. And if I go from 9 to 3, that's 3 divided by 9, which is also a ratio of 1/3. And if I go and look at the next ratio from 3 to 1, that's also a ratio of 1/3. And so, yes, this is a geometric sequence. In this case, the ratio is the number 1/3. 1/3 is what you multiply each of those numbers by to get the next one in the list. In these next two examples, notice how there's some alternating signs every once in a while. That can happen with geometric sequences. That does not happen with arithmetic sequences. Let's look and see if there's something we can multiply each of these numbers by to get the next one. If I start with 4 and I double it, I get 8. If I take 4 and I multiply by -2, then I get -8. And so the ratio for these first two terms is -2. And if you take -8 and multiply it by -2, you get +16. And if I take +16 times -2, I get -32. And so this is consistently multiplying by -2. And so yes, this is geometric. And the ratio this time is -2. And if I look at our last example, to go from 3 to 9 is a multiple of 3, ratio of 3. To go from 9 to -27 is a multiple of -3. And so I can throw this out right now. It's not going to be geometric. It doesn't go up by the same amount each time. From 27 to 81 is multiplying by 3 again. To go from -81 to +243 is to multiply by -3. And so there's kind of an interesting pattern, and it's like pseudo-geometric. It's at least multiplying by 3 each time gets us the numbers, but those signs are a little bit goofy. So technically, this is not a geometric sequence. Now, a huge skill required for this section is to be able to take a sequence and write a rule for it. And like our arithmetic sequences from yesterday, there's a template that you can use all the time. This is what's provided in the book. So the rule for a geometric sequence is to start with the first number in the list, multiply by the ratio raised to the n minus first power. And that's a fine template. I don't like using this so much because it gets kind of sloppy with the n minus 1 in the exponent like that. A variation that I like that you won't find in the textbook is to go backwards a step and figure out what the 0th number in the list is. And if you're willing to do that, then you don't need the n minus 1 in the exponent. You can just take the 0th number times the ratio to the nth power. And so we'll use both of those templates as examples today, but personally I use the template in blue a little bit more often. So in this first example here, the sequence of numbers starts with -8 and then goes to -12, -18, -27, and in order to write a rule for this particular sequence, we need to use one of the templates. And so if we go ahead and write down a template, an is equal to something times something to the n minus first power. I need to figure out what the first number in the list is and what the constant ratio is. So the first number in the list is relatively easy. That's the -8 that's here. The ratio in between each individual term is not quite as obvious. What times -8 gives me -12? What times -12 gives me -18? What times -18 gives me -27? My brain's not figuring that one out super easy, so I'm going to use the divide by trick. The ratio is -12 divided by -8. And that ratio is positive. The negatives cancel out. 12/8, and 12/8 reduces to 3/2. And so one potential formula for this is -8 times 3/2 raised to the n minus first power. And if you're going to type that into a calculator, you got to be careful. The 3/2 and n minus 1 is not easy to type correctly. There's a lot of places where you can make a mistake. You really need to put the 3 minus 2 in parentheses and then the n minus 1 in its own set of parentheses as well, or else if you plug a specific number in for n, do that subtraction first. So anyway, here's a formula. Again, like in our last unit, there's lots of potential ways we could tweak this or rearrange it a little bit that might still work. But then we were asked to use this formula to calculate the 8th number in our list. And so, like yesterday, that means plug in an 8 for n and see what comes out. So -8 times 3/2 raised to the 8 minus first power. And that means -8 times 3/2 raised to the 7th power. And so if you want to type that into your calculator, be careful with the parentheses, but you can type that in. I ended up with the decimal -136.6875, but a lot of times it's a little bit nicer to convert that into a fraction. On the TI-83 and 84 calculators, you can hit math fraction, and it will do that for you. This came out nicely to -2,187/16. And so that's what a to the 8th is. I might recommend hit pause for a moment and see if you can write a template for number 3. And in just a moment, I'll put what I had down as a final answer there. using the black template, the one from the book, the first number in the list, A1, is number 5. And when you divide each of those individual terms, the ratio each time is 2/5. And so formula is to take 5 and multiply it by 2/5 to the n minus 1. And the second part of this question was to calculate what A8 is. And so that means, again, plug in an 8. And so that is 5 times 2/5 to the 8 minus 1. 8 minus 1 is 7th. And so you could go straight to the calculator and type this in. Another thing you can do, if you want, is distribute that 7 to the number on top and to the number on the bottom. And by doing this, sometimes you can work with fractions and clean it up a little bit nicer that way. Notice the 5 that was the initial number, and the 5 to the 7th can be cleaned up a little bit. We could reduce that to 5 to the 6th. And then each of these things could be calculated one at a time. 2 to the 7th power is 128. And 5 to the 6th power is 15,625. And so that's just another way of looking at it if you don't want to use your calculator. Now, different set of questions that's a little bit more challenging is to write a rule for a particular term when you don't know what the first number is in the list. And so, like we did last time, I would start by writing out a template and then filling in the various things that we do know, but you'll probably have to solve for the 0th term or the first term or whatever part of the template that you don't know. And so in number 4 here, we want to write a rule for a geometric sequence that's doubling each time, that has as a third term 5. And so if I write out a template, and I haven't had a chance to use my template yet, so I'm going to use my template. AN is equal to A0, A0, the 0th number in the list, times the ratio raised to the nth power. And so in this particular case, we were told when n is a 3 that AN is 5, and so AN is 5. The 0th we don't know. We don't know the first number in the list or the 0th number in the list for that matter. We do know the ratio though. Ratio is 2. Oops, let me actually write it 2 and not the letter R. It's kind of strange. So 2 to the 3rd power. And then 2 to the 3rd power is just a number. We can figure out what that is. 2 to the 3rd is 2 times 2 times 2 is 8. And so a to the 0th is what I get when I divide both sides by 8. And so a to the 0th is 5/8. And so that number by itself isn't our answer, but when we put that number into our template and the number 2 into our template, then we've got an equation. AN is equal to 5/8 times 2 to the nth power. And if you had used the other template, you would have gotten a slightly different answer. Using the other template, instead of looking at the 0th number, you would have looked at A1, and you could have calculated that that was 5/4. But then instead of having just a nice clean 2 to the n, you'd have 2 to the n minus 1st. And so both of these formulas work. If you plug in a 3, they're both going to give us out a 5. And if you plug in other numbers, they're always going to be ratios of multiplying by 2 each time. And so neither one's any better than the other. I just like the blue one because it's a little bit cleaner. Again, I don't like that n minus 1 in an exponent. It's a little hard to work with. So on the other side, we can do the same sort of moves. If we start with my template, an is equal to the 0th number in the list times the ratio raised to the nth power. Then for this problem, they told us the 4th number in the list, and so n is a 4. They told us the ratio is 3, so 3 to the 4th power. A naught is unknown. We'll have to calculate that. And A4, the 4th number in the list, is a 3. And after solving this, 3 to the 4th is 81. And so if we divide both sides by 81, then we get that the 0th number in the list is 3/81. 3/81 is the same thing as 1/27. And so combining the 1/27 with the 3, we can write a template, or write a rule, excuse me. An is equal to 1/27 times 3 to the nth power. And there's a lot of different ways that we can write this one, especially since 27 is a power of 3. You could write it as 3 to the negative third, and then combining 3 to the negative third with 3 to the n. I wouldn't be surprised if you see, for an answer for this one, something like 3 to the n minus third power. Some textbooks might think that that's easier to work with, and I might agree with them in this case too. But the overall rule, or the general principle, is whatever formula gets you the right numbers is correct. There might be a nicer, more convenient way to write that, but if it's giving you the right numbers, fine. It's good to go. In these last examples, the hard part here is that they haven't told you what that ratio is, nor have they told you what the first or last term in the sequence is, and so you have to find both of those different things. And so when we did questions like this with arithmetic sequences, we talked about how the common difference was kind of like a slope, and you figured out the change in n and the change in y and rise over run sort of thing to find difference. We can do a similar thing with ratios, and that is if we take the ratio of the terms that's given to us. In this case, they told us the 5th term and the 2nd term. If we divide those things, that's going to be whatever the ratio is to the 5 minus 2nd power. So, substituting in the numbers they told us, the 5th number in the list is negative 1,215, and they want the 2nd number in the list to be 45. If we divide those out, that's going to give us what r to the 5 minus 2nd power is. And so 5 minus 2 is 3. And so if we divide negative 1215 by 45, we get out a negative 27, and that's equal to r cubed. Taking the cubed root of both sides gives us negative 3. And so the ratio that's required for this problem is negative 3. And now it's a problem similar to our last problem. You can use a template and plug in some numbers and so forth. This one might be easier to actually write out just a few blanks and figure out what the 0th of the first term is. They said that the 2nd number in the list is 45. That the 5th number in this list is negative 1,215, and the ratio is to multiply by negative 3 each time. So 45 times negative 3 is negative 135, Negative 135 times negative 3 is 405. And just to double check, 405 times negative 3 is negative 1215, and so that's good. If we were to work this pattern in reverse, we would divide by negative 3 to go backwards a step, and we could divide by negative 3 again to go backwards another step. That would get us the 0th number in the list. And so 45 divided by negative 3 is negative 15. Negative 15 divided by negative 3 is positive 5. And if I know the 0th number in the list and the common ratio, you can write a template or write any formula using the template. 0th number times common ratio raised to the nth. And so the 0th number was 5, and the common ratio was the negative 3. What a mess. Let's clean that up just a little bit. So the nth number is 5 times negative 3 to the nth power. Now, after all that work, it's probably a good idea to plug in a 2 for n and make sure we get out a 45, and plug in a 5 for n and make sure we get out negative 1,215. So I'll go straight to the last one there. 5 times negative 3 in parentheses. If you're typing it onto a calculator, 5 times negative 3 in parentheses raised to the 5th does give us negative 1,215. So, yep, I'm confident that this formula works. Is it the one that's in the back of the book? Probably not. But that's it is a formula that works. It gives us A2 and A5. If we repeat these steps with question number 7, here A2 is negative 4, and A to the 6th, or not A to the 6th, but the 6th number in the list is 1,024. And so if I take those numbers, A6 and A squared, and divide them, that's negative 1,024 divided by negative 4. That works out to 256. And the key is that that's equal to our ratio raised to the 6 minus second power. And 6 minus 2 is 4. And so 256 is equal to r to the 4th power. And if you take the 4th root of 256, it's actually two possible answers, two possible ratios, two different sequences that we could write for this. Those two would be the positive 4th root of 256, and that's 16. Oops, I'm sorry. That's the square root of 256. I've pushed the wrong button. I'm sorry. 256 raised to the 4th power. There we go. I had to actually type in 256 raised to the parentheses 1/4 power to get that on my calculator. The calculator gives us a 4, ratio of 4. Technically, a negative 4 to the negative 4th power would also, or negative 4 to the 4th power would also work. That'd be kind of interesting that the signs would alternate. And they didn't specify whether or not they wanted that or not. So really, either of those options could work. I'm going to keep it simple and go with a positive 4 as a ratio. And so if the second number in the list is negative 4, and the third number in the list is whatever negative 4 times 4 is, and 4th number, 5th number, 6th number should be negative 1,024. What I really need is either the 0th or the 1st number in this list. And going backwards means I'll divide by the ratio of 4. So negative 4 divided by 4 is negative 1. Negative 1 divided by 4 is negative 1/4. So the 0th number in the list is negative 1/4. And I can write a rule now. The 0th number in the list times the ratio raised to the nth power is negative 1/4 times 4 raised to the nth. And again, probably could take this formula and rewrite it in a lot of different variations. The key to whether this is acceptable or not is, does it give us, when we plug in a 2, does it give us a negative 4? And when we plug in a 5, does it give us a negative 1024? And so if you type negative 1/4 times 4 raised to the 5th power, I actually didn't get the right number. What did I do wrong? Oh, that's what I did. I was thinking about the 5th number. 1024 isn't the 5th number in the list. It's supposed to be the 6th number in the list. So plug in a 6 for n. Let me try that again. Negative 1/4 times 4 raised to the 6th power. Yeah, there we go. Negative 1024. So we did have the right rule. I just checked it wrong. So anyway, there's a couple examples of taking various geometric sequences and trying to work their formulas out and so forth. And so please go ahead and try the problems down at the bottom from your book, and I will see you tomorrow.